Alright, so today's just a wrap-up day. We've been looking at things from a physical perspective. So things are best represented in a physical sense with parametric equations and vectors, because we want to isolate the horizontal behavior from the vertical behavior and relate it to time. So I just need to give you a couple definitions, and you'll apply these definitions to the questions for tonight. The first, you already know. We define the velocity vector as dx dt, so the derivative of x with respect to time, and dy dt. So we're isolating, in terms of time, the vertical and the horizontal behavior. So we've already talked about that. Just in terms of then vocab. How do you find the displacement? In terms of, we know what displacement is as a definition, but how do you do it in terms of a vector? And so if you're going to do displacement, you need bounds. And so your bounds are going to be from the starting points A to B. So how do you do the displacement in terms of x, and how do you do the displacement in terms of y? And so we need to do the antiderivative of the velocity vector. And so we'll go as an antiderivative from A to B of dx dt. So that'll be the displacement in terms of x. And then the antiderivative from A to B and the displacement in terms of y. Okay, the displacement doesn't just tell you where your final position is, though. It just tells you the difference between where you started and where you ended. And so then you've got to talk about, well, where did I start and where did I end? So if we're talking about a starting point, okay, that's also called not just called the starting point, but called the initial position vector. At A. And so that would be just x sub A and y sub A. So where are we starting from? At the beginning of this interval where time is A, where do we start? So then our final position takes that into account. And so the ending point that'll be the final position vector by definition at time A. So that would be a combination of the displacement and the initial position. So you're going to add those two together. So you take your x sub A, which is your initial position, you'll add to it the displacement over the bounds from A to B. So that'll be the vector for the final position for the horizontal position. And then the same thing for y. We take our initial position, and we add to it the displacement from A to B in terms of y with respect to time. All right, and then the last definition, so this is all physics stuff. So we talked about displacement. Displacement is the difference between the starting point and the final position, but then that's not necessarily the same as the total distance. So do you remember back when we were talking about that in the first place? How did you do total distance in terms of Cartesian? Yeah, you need an absolute value. And so the same thing is true here. Okay, the total distance would be going from A to B, the absolute value of the velocity vector with respect to time. And the definition of the absolute value is the magnitude. So this will be the integral of the square root of the components of the velocity vector squared individually. So the square root of the x dt quantity squared, and then the y dt quantity squared with respect to time. And so since the absolute value of the velocity is the same thing as what we call the magnitude, you're going to do the integral of that to find the total distance traveled over the closed interval from A to B. So those are just all the definitions that you'll need to apply those to some word problems, some actual physical problems tonight, of different, planes moving and balls moving and things like that. So very similar to what you did yesterday, but you just need to know the definitions so that you can set up the integrals to solve.